Welcome back, everybody. So we've talked about the real number system. What we want to do now is move into what's known as the complex number system. Now, you may think that with the real number system, we've exhausted all types of numbers that are possible. And for a long time, that's really what people thought. But it's actually not the ultimate umbrella. Let's think about the equation x squared equals -1. Typically, most students think that when you square a number, you're going to get something non-negative, right? A positive times a positive is positive. A negative times a negative is positive. And then 0 times itself, of course, is just 0. So when we're squaring, we somehow can't get negative numbers. But really, you're limiting yourself in the types of numbers you're allowing yourself to square. It is absolutely true that any real number squared will be non-negative. But is there another type of number that when you square could give you a negative? And perhaps more particularly, give you -1? And the answer is yes. And that type of number is known as an imaginary number. And when we put those together under the larger umbrella of complex numbers, we get a set of numbers with wonderful implications and properties in algebra. So let's go ahead and move into our discussion of complex numbers. Okay, so thinking back to, let's see here. So thinking back to that equation that I mentioned, x squared equals -1. Again, most algebra books would describe this equation as not having a solution, but it's very misleading. If you say that it doesn't have a solution, it depends on really where you're looking. If you're looking in the real numbers, then no. But if we have ourselves a little dip in that pool of imaginary numbers, then oh, yes, indeed. So what is an imaginary number? Well, it's defined as the square root of -1. Now, I want to have a comment here about why they're called imaginary. A lot of people, especially people who buy into the whole, when am I ever going to need math? It's in vogue to describe all the woes that you have with math. They might say comments such as, well, gosh, it's imaginary, sir. Now we're talking about things that don't even exist. Well, let's not be in such a hurry to sound so ignorant. Imaginary. Just think about the evolution of our number system. By the time we were dealing with numbers involving the square root of -1, the term real number was already taken. But this is not a number that's contained in that set of real numbers, so we needed a name for a number that is not a real number. Seems like a natural choice to call it imaginary, okay? All right. So let's see how these work. We're going to compute some powers of I. I to the first, of course, is just I. I squared, well, remember, I is the square root of -1. So if I square the square root, I'm left with -1. And then I cubed. Watch what I'm going to do with I cubed. I'm going to call that I squared times I. We know I squared is -1, and so I cubed is just -I. I to the fourth is I squared times I squared, which is -1 times -1, which is 1. Okay, so so I to the first is I squared -1 cubed -I, the fourth 1. Okay. What about I to the 17th? Well, we could play a similar game, right? I could take I squared times I squared times I squared times I squared if I wanted. Or I could take I to the fourth times I to the fourth. And that might be a better choice because we know that I to the fourth is actually 1. So look what I'm going to do with 7 to the 17th power here. I'm going to write that as 4 times 4 plus 1. 4 times 4 is 16 plus 1 is 17. Now, why did I choose to do this? Well, because I can break it up, right? Simple laws of exponents. And then I to the 4th times 4 is really I to the 4th to the 4th times I, which is just 1 to the 4th times I, which is just I, okay? By the way, what's the remainder when you divide 17 by 4? Ask that again. What's the remainder when you divide 17 by 4? Oh, the remainder is 1. What do you know? All right. How about this one? I to the 21,784. Well, really, I want to know how many times does 4 go into 21,784? Well, so let me mention that. So, you know, you could take a calculator and just divide 21,784 by 4, or you could make some argument from, you know, just what you know about, you know, how to divide numbers and look at that last spot. You know that 4 goes into 80, so it's going to go into 84 and so on. But will it go into 784, right? Let's just take a look here. So what I would encourage you to do, and I'm going to have you pause it, is write 21,784 as 4 times something plus something. In other words, to be completely old school, go back to yesteryear. Remember this old long division? Can't believe I'm doing this, right? 21,784. Let's see here. So 21, so that's 5. That's 4. That's 4. 4 goes into 24 6 times. So yeah, it goes in, I'm sorry, not plus 1, plus something. What's the remainder? And so we get 5,446. Well, what does that mean for us? That means that I to the 21,784 is actually I to the 4th to the 5,446, which is 1 to the 5,446, which is just 1, okay? Now, how about G? I to the 4K plus 3. Well, we know that, right? And I to the 4K, right? Any multiple of 4 in my exponent is just going to give me 1, right? I to the 4th is 1. So 1 to the kth power is still going to be 1. And we know that I cubed is negative I. And so we get negative I, okay? So what's important to recognize here is that powers of I are going to be one of 4 different values: I, -1, negative I, or +1, okay? All right. We're now ready to talk about the complex numbers. There are any numbers that can be written in the form a plus bi, or a and b are real numbers. The set of all complex numbers is denoted by the symbol C, that fancy C, just like all our other sets. Much like X is often used to denote a real variable, Z is often used to denote a complex variable. Okay, it's just kind of a convention. So here's some questions for you. Is every real number a complex number? Well, give me a real number. All right. I'm sure someone out there was thinking 2. Well, 2 can be written as 2 plus 0i. So is 2 a complex number? Yes. If x is a complex number, I'm sorry, if x is a real number, I could write it as x plus 0i and still, right, that's a real number, but now I've written it in a form that indicates it's also a complex number, okay? So yeah, the real numbers are contained subset of the complex numbers, okay? And then B, are imaginary numbers and complex numbers the same? Now I'm asking this because there's a bad habit. A lot of times people will use them interchangeably, and that's just not the case, okay? The answer is no, okay? Imaginary numbers, like something, like say we had something I, those could be written as 0 plus ki. So just like the reals are a subset of the complex numbers, the imaginary numbers are also a subset of the complex numbers, okay? All right. So we want to do a little bit of algebra here, arithmetic even. We want to write these in the form a plus bi. That's the standard form of writing a complex number. And so let's go ahead and do that with these next few examples. So a, we have 2 minus 3i all over 7. That is not in the form a plus bi. But if I rewrite it like this, now it is, okay? And you might say, well, that's not plus. That's okay, right? Plus negative 3/7. We'll write it as minus 3/7i, okay? 3 minus 5i times 1 plus 3i. Well, here it's not so simple, but we're going to see a result in our next definition that kind of works out nicely. So I'm going to take this 3 minus 5i times 1 plus 3i, and I'm going to multiply it by 1 plus 3i over 1 plus 3i. Okay. Now when you multiply these, I'm sorry, not 1 plus 3i, multiply by 1 minus 3i. Now when you multiply these, this is just like multiplying, they're binomials. You're multiplying binomials essentially. So my numerator, I'll have 3 times 1 is 3. Negative, right? 3 times 1 is 3. Negative 5i times 1 is negative 5i. 3 times negative 3i, negative 9i. And then negative 5i times negative 3i would be positive 15i squared. Okay. Now my denominator, interesting thing happens. I get 1 plus 3i minus 3i minus 9i squared. So keeping in mind that I squared is really negative 1, then I get 3 minus 14i minus 15, right? I squared is negative 1. And then in my denominator, 1, well, I squared is negative 1. So negative 9 times negative 1 is positive 9. All of a sudden, I have a denominator that is real, which means I can actually, if I want to reduce this first, I guess I could do that. Now I can break it up. Negative 6/5 minus 7/5 I. We now have the form a plus bi. So kind of interesting that when I multiplied 1 plus 3i times 1 minus 3i, I wound up with a real number, no longer complex, no longer with an imaginary part. Taking advantage really of the fact that the 3i's are going to cancel each other out.
All right, last one, 3 plus 4i quantity squared. Well, this means 3 plus 4i times 3 plus 4i. And so just like you would multiply binomials, you're going to multiply these. So 3 times 3 is 9. 4i times 3 is 12i. 3 times 4i is 12i. And 4i times 4i is 16i squared. So we get 9 plus 24i minus 16, right? Because again, this I squared is really -1. And so what is that? -7 plus 24i. Okay, there we go. Well, we took advantage of something interesting. We took advantage of what's known as the complex conjugate. The complex conjugate of a plus bi is a minus bi. In other words, the imaginary part just has the opposite sign. If I'm letting z be a complex variable, then the conjugate is z bar, a z with a bar on the top, okay? And what I want to do is prove that the product of a complex number and its conjugate is a real number. So watch how this works. Let a plus bi be a complex number. Now, when I say that, implied in this is that a and b themselves are real, right? A and b are real numbers. Well, I'm multiplying a plus bi times its conjugate, a minus bi. When I do that, I get a squared plus abi minus abi minus b squared times I squared. Well, notice the abi minus abi, right? Those are gone. I get 0 I. And then minus b squared times -1. A squared plus b squared. Now, a squared, right? That's real. B squared is real. So I have real plus real. That is a real number. The imaginary part is gone, okay? And that proves it. Okay, so let's finish up here by going back to that Venn diagram, right? Last time we said, okay, you've got, I'll build it from the inside out. You've got the natural numbers. The natural numbers are contained in the integers. The integers, let me give myself some more. The integers are contained in the rationals. Outside the rationals, you've got the irrationals. And then together, you've got the real numbers, okay? But we could go further, right? We could also say that inside the complex numbers are the real numbers, right? So really, there's this whole other set that contains the reals, okay? And of course, anything outside of the reals, but inside the complex would be strictly imaginary, okay? All right, so we have developed all the numbers we're going to need for this class. Keep in mind that the purpose for talking about these different numbers, number sets, real numbers, complex numbers, is that we're going to talk about functions. We are now ready to do that. We are going to define functions on these sets. And so that is where we go next. And until then, once again, happy studies.